hydroforming, as shown here. Hydrostatic pressure from inside the tube forces convolutions into the dies, shaping the bellows. Residual stresses that can contribute to stress corrosion cracking are minimized with hydroforming. Usually either flanges or pipe weld ends are then welded to the bellows, which anchors expand without added flexibility. The loads on the anchors will likely be too much for the system to withstand. We see here a model of a pipe run with anchors on either end. Note that the anchors are shown close together just for visualization here in our pipe system model, but in any real system they would be very far apart. If we first remove the anchors and the pipe heats up, as indicated by the rising thermometer level, the pipe grows as shown. When the pipe anchors are added and the pipe again heats up and begins to expand, the immense thermal load on the anchors will build until they fail. Now when we add an expansion joint between the anchors, as the pipe heats up and expands, the joint compresses to compensate for the movement, and there are now minimal thermal loads on the anchors and pipe. Although applications are not always this straightforward, most are a variation of what we see here. Adding metal joints is often a key way to handle expanding hot pipes. Metal joints usually have a stainless steel bellows with multiple corrugations that provide them with the ability to move. They can achieve long lives even in the higher temperatures and pressures of demanding systems, such as steam and many others. The bellows are manufactured by mechanical forming methods, or preferably through hydroforming, as shown here. Hydrostatic pressure from inside the tube forces convolutions into the dies, shaping the bellows. Residual stresses that can contribute to stress corrosion cracking are minimized with hydroforming. Usually either flanges or pipe weld ends are then welded to the bellows, which turns it into an expansion joint. There are three movements that the joints can make: axial compression or extension, lateral offset, and angular deflection. As we have demonstrated, the most common movement is axial compression, due to a straight run of pipe heating up. But solutions and planning for other movements may be needed as well. And there are different types of metal joints with different options to consider. Stainless steel, while the ends are most commonly carbon steel, depending on the piping material. Primary options for this type of joint include liners and covers. Liners are usually slipped in to provide either erosion protection or for high flow rates to prevent flutter. Covers protect the thin bellows from potential damage where that may be a concern. The optional tie rods limit the extension and sometimes the compression of the joints. The rods loosely fit through holes in lugs that are welded to the flanges or weld ends at Flexicraft's factory, and nuts on the rods prevent them from going through the lugs. Although the single bellows joints are the most common, they do not move very far in lateral offset. For large lateral movements, a universal configuration with two bellows is needed. The longer the center pipe spool, the more lateral movement is possible. As closing allows the system's fluid to pressurize the bellows from the outside, it is more stable and can be made longer to allow considerably more compression.
Now that we've added some context with an overview of metal expansion joints, we can take a moment to go over the often misunderstood and important topic of pressure thrust load. This new anchor support load can be difficult to understand at first, but it's critical to both the choices between products and also how they're applied. When you add an expansion joint to a pressurized piping system, you are introducing this new pressure thrust load to the piping anchors. This new force on the anchors is a main reason why you shouldn't just cut a hole in an existing pipeline and add an expansion joint, even though the large thermal anchor loads from the pipe growth would be minimized. So what exactly is pressure thrust load? To understand it, we can start by looking at a bendable straw example, where the bending section represents an expansion joint. If one end of the straw is plugged, and if we could blow into the other end hard enough, what we would see is the bendable section getting stretched out. The force on the plug from the pressure would force apart the bendable section, but not stretch the rest of the stiff straw. That pressure force acting on the plug is the thrust load and is equal to the pressure times the cross-sectional area. We can now go back to our pipe system model at first without the anchors. This time we pressurize the pipe instead of heating it up. The pipe acts as though it's plugged with the thrust load acting on both ends because of elbows and other ends down the line. Notice there is no movement of the pipe because the pipe wall is too stiff to be moved by the thrust load. But if we cut a hole in the same pipe and add an expansion joint, we have a model like the bendable straw. Now when we again pressurize the unanchored system, we can see the joint will stretch out to failure because it's not stiff like the pipe. When we now add back the pipe anchors and again pressurize, the joint does not stretch out from the thrust load because the anchors are preventing that. But if the anchors are not designed to withstand the new load, they can fail and consequently then allow the joint to stretch out and also fail. Tie rods are sometimes added as an attempt to absorb the thrust load so the anchors don't have to. The issue with this approach in a straight pipe run is that if the joint compresses, the nuts attached to the rods will separate from the lugs. When they separate, they no longer shoulder the load. So trying to use tie rods to handle the thrust load only works if axial movement isn't needed. And we have seen this isn't the case much of the time when thermal pipe growth is involved. Let's take a look at this on our pipe model. We see the pipe system first get pressurized quickly before heating up. At this point, the tie rods are working to absorb the thrust load so the anchors don't have to. But when the system starts to heat up, the tie rods disengage from the lugs as the joint compresses, and the thrust load gets transferred to the anchors, possibly causing them to fail as before. So what is the solution to the new pressure thrust load? Well, one solution is to simply ensure the anchors are large enough to withstand it, as we see them getting larger here. Now when the pressure and temperature both rise, the system works as it should. So the anchors must be designed for the force of the thrust load, which is equal to the effective cross-sectional area of the bellows multiplied by the pressure. In addition to the thrust load, a second load, the spring load, is added to the anchors when the
Metal flanges, often with tapped flange holes, and a rubber lip. Backing rings are split and easily removable. They have arches that can be filled to provide a smooth bore, or additional arches can be added for greater movements. Integral Teflon liners are also available that conform to the arch. Tie rods, as part of control units, are often used to control the thrust load. Unlike tie rods for metal joints that are welded to the joint flanges or ends at the Flexograph factory, rubber joint rods must be installed in the field. After the joint is placed in the pipeline breech and partially bolted up, the gusset plate lugs parts of the control unit are bolted on the outside of the mating flanges to complete the installation. Because they are not technically an expansion joint. That is to say, they are not meant for axial compression or extension because of the braid. But the braid does provide an advantage. Primarily, the braid can withstand the thrust load because of its axial stiffness and extension. The braid essentially acts like tie rods. And because these are most often used on pumps and other equipment as flexible connectors, eliminating the thrust load on the equipment nozzles, which act as anchors, is often critical to pump performance. Although they cannot absorb thermal growth compression, they can move for lateral offset and absorb vibration well. Flexible pipe connectors are usually either braided metal types or spherical rubber joints with tie rods as previously discussed.